Here we're looking at the banked curve. This is a really fun scenario. So you see this if you're into sports racing, you'll see this lots of times. And also if you ever go on a highway, you'll notice that sometimes the exits or on-ramps are slightly banked. Also, if you ever drive, maybe you probably have not, but apparently if you drive to more rural areas or places that have lots of snow, you'll see there's curves that are banked. So what allows us, what we saw in the first friction question making a turn, is that friction was what allowed cars to make a turn. But now when you have a banked turn, force of gravity is also helping you make that turn. Not force of gravity directly, because it's actually the normal force. So first thing we need to recognize when we have a banked turn is, where is the center of the circle? So lots of people get mistaken with this at first. People want to say, oh, the center of the circle is down the hill. No, that's not true. The center of the circle is not down here. The center of the circle is actually just directly to the left of the car in this scenario. The center is just over here somewhere. So this is our centripetal force. It has to be pointing towards the center of the circle. So we're saying, how does all our individual forces, or this is our net force, how does our net force equal to all our sum of the forces? Yeah, if you don't really understand why this centripetal force is directly to the left, try Googling some YouTube videos. Just look up bank turn, and you'll see that a picture from the top view, what is actually happening. If you look at this top view, this thing's not moving up or down. It's staying in that constant level horizontal plane, and it's traveling around a circular path. So we have force of gravity is going downwards. That's Fg. Normal force is up and to the left. So those are actually the only two forces acting on this car. Yes, there's probably into the plane, there's definitely some type of force of engine making it move, and there's force of friction or some other types of air resistance opposing it, but we're only interested in these forces because we're trying to see what is causing that centripetal force. So for this first one, we're going to ignore friction, and we'll look at friction scenario right after. So we're going to use the axes. This up is going to be positive, left is positive. That's what we're going to use for x and y. So what we can see is our normal force. Here's our normal force, can be divided into two components: the x component and the y component. So if this is theta right here, it comes out to be that this is also theta. If we do a little bit of geometry, let me just draw it in right here. If that is theta, sorry, let me draw this a bit bigger actually. I'll draw it over here. So if this is, just say pretend this is 30 degrees. If I were to draw a line straight down, this would be 60 degrees. And I need that normal force is perpendicular to the surface. That's 90 degrees. So this is 60. This must also be 60. And therefore this must be 30. Okay, so whatever angle there, that's also the same angles. 30 degrees, 30 degrees. Theta, theta. So what we can see from here though is that the y component of our normal force is going to be Fn cos theta. And our x component is going to be Fn sine theta. So from here we get two equations. In the y direction, we can see that we know this thing's not moving up or down. So we know our net force, F net, in the y direction must be equal to 0. And what is making it equal to 0? Fn cos theta upwards minus force of gravity must be equal to 0. So that is one equation that we have. In the x direction, we have F net in the x direction. That must equal to our centripetal force, because if we look at our, compare our net force diagram and our sum of the forces, net force is just to the left. Net force is the centripetal force. And the only force that is causing that centripetal force is that Fn sine theta. So those are our two equations. So I'm just going to redraw this because I'm running out of space. I'm going to write those two equations again. So in the y direction, we get 0 is equal to Fn cos theta minus the force of gravity. And in the x direction, we have the net force is centripetal force is equal to Fn sine theta. So this is, simplify these a bit. Fg is just mass times gravity. It's equal to Fn cos theta. And in the x direction, we get mv squared over r is equal to Fn sine theta. So we have two equations. And now we're just going to do, now it's just math. Can we solve these expressions? So what we can see is, if we divide these two equations, just do a little bit of substitution. I'm going to use the dividing method. So I'm going to take equation, here's equation 2, here's equation 1. So I'm going to take equation 2 and divide it by equation 1. So when I divide Fn sine theta divided by Fn cos theta, we end up with tan theta on the right side of the equation. And on the left side, the masses are going to cancel out. Still have v squared over rg. Okay, so that's what we get when we do a little bit of algebra to combine them. Now we can just solve for theta. Theta is equal to inverse tan v squared over rg. And if we plug in our values from our question, 13.4 meters per second, radius 50 meters, gravity 9.8, you get 20 degrees. So when you are traveling around a banked turn, if there's no friction, you need to travel at a very precise speed to navigate it. However, with friction, it gives you like a range of possible values, and that's what we're going to solve for in the next problem coming right up.